everyone. Good morning. A new topic today. I think we've probably flogged that poor horse of increasing, decreasing, concave up and concave down to death. We are going to look at what are called indeterminate forms, but more importantly, we're going to show you a new way to find limits called LHospital's rule. And let's do the first topic. Certain calculations in mathematics are called indeterminate form. Essentially, that means that we do not know, unless we have more information, what the answer is. So I'll give you examples of indeterminate form. 0 divided by 0 is not 1. 0 divided by 0 is indeterminate form. It might be 1, but it might be 42. It might be 0 and it might be infinity. We need more information. Infinity over infinity is indeterminate form. Zero times infinity is indeterminate form. Right? You can't tell unless you have more information what that eventually will be equal to. Almost all of these indeterminate forms come from finding limits, right? You find a limit and the top's infinity, you find a limit but the bottom's also infinity, because it tends to be fractions as well. But there are some unusual ones. Infinity take away infinity is indeterminate form. So these are situations where you don't really know what the calculation is equal to. We call them indeterminate form. These are not to be confused by the following calculations. 0 over infinity is not indeterminate form. Infinity over 0 is not indeterminate form. Infinity times infinity is not indeterminate form. And infinity plus infinity is also not indeterminate form. What do I mean by that? It means I know what these are equal to. If you have 0 on the top and you divide it by infinity, what will the answer be?
0.
Yeah. I mean, you could say really 0 if you wanted to emphasize it, but it's still 0. Now, infinity is on the top. We're talking positive here. Infinity is on the top and it's being divided by 0. What's that calculation going to get you? No takers? Infinity over 0. It's equal to something. Last chat. It's still equal to infinity. Infinity divided by 5 is infinity, right? 1 divided by 0 is infinity. So infinity divided by 0 is just a really, really big version of infinity then, isn't it? It's just still infinite. Now, if you take infinity and multiply it by infinity, you would get infinity. And if you take infinity and you add infinity to it, you still get infinity. So these guys are not indeterminate form. And that's the concept of indeterminate form. That there are certain calculations involving zeros and infinities, right, where we do not know the answer unless we get more information. And these combinations are called indeterminate form. There are other combinations of 0 infinity where we actually do know what the answer is going to be. Most of the time, isn't the answer going to be 0 or infinity, depending on what the calculation looks like. We cool with that new idea, this thing called indeterminate form, and when we would recognize it. So let's show you what LHospital's rule is. believe he was a Belgian, not very many Belgian mathematicians, but he was one, I believe. I've never really found out the correct pronunciation. I call it LHospital because someone corrected me once, and I've also been told that I'm wrong. It's LHospital and the S is there. So whatever way you want to pronounce it, LHospital or LHospital, this is the guy who came up with a way of finding limits. He found a way of finding limits of fractions. There are three kinds. You get the limit as x tends to 0 of a fraction, right, some function divided by some. You get the limit as x tends to infinity of some fraction. And then you get the limit as x tends to a number, I'm just picking 3 as an example, of some fraction. And L'Hopital's rule says, if you plug 0 into this fraction and you get an indeterminate form, then you're allowed to use L'Hopital's rule. So let me say it again. If you plug in the numbers into these calculations, right, and it ends up being indeterminate form, then you're allowed to do the following calculation. You're allowed to do this. And this is amazing and not very intuitive. The limit as x tends to 0 of two functions divided is the same thing as the limit as x tends to 0 of the derivative of those two functions. Now notice that is not a quotient rule. That's just take the guy in top and differentiate them, and totally independent differentiate the bottom. And he found out that for every single one of those situations that I've written down, this is true. So as long as it's indeterminate form, you can find the limit to this guy, and it's going to be the same answer as the limit to the original. You might think, well, why is that even vaguely useful? Sometimes you do this guy and you can't get an answer because it looks like one of these guys, right? It's indeterminate form. But when you differentiate the top and the bottom, very often this guy is doable. In other words, the top's 4 and the bottom's 3, and now you know the answer. Or the top's 4 and the bottom's 0, so the answer's infinity, right? Or whatever the combination might be. So that's what L'Hopital's rule does. So let's show you L'Hopital use being used. Let's do the limit as x tends to 3 of x squared take away 9 over x take away 3. Now, first thing you do is you check that you're allowed to use L'Hopital's rule. I'm going to do something here. We're getting some feedback that I don't want. There we go. So first we check. If you plug 3 in here, the top's 0, the bottom's 0. Ah, great, indeterminate form. You put equals and you put a little L above it. That's the normal notation for saying I'm using L'Hopital. And now you find the limit as x tends to 3. Well, if you differentiate the top, you get 2x. You differentiate the bottom, you get 1. And now you can do 2 lots of 3 over 1, and the answer is 6. You remember back, I think it was in week 1, might have been early week 2, didn't we do those by the factor and cancel method? Isn't this cleaner? You don't need to factor things, you just differentiate. Now, sometimes when you differentiate using L'Hopital's rule to get this guy still doesn't work, right? You get an indeterminate form. But well, L'Hopital says, that's okay, just do it another time, right? Just differentiate again. And if you need to, sometimes you have to even do it a third time. But eventually something will happen. How about this fella? This is a version question 3. So it's going to be the limit as x tends to 9 of the square root of x take away 3 over x minus 9. Now, if you were going to do that the old-fashioned way, right, this one would be factor and cancel. Can anybody remember what the name we give to this method?
Conjugate method?
Right. Wasn't the conjugate, I mean, it was doable, but wasn't a bit clunky. You had a lot to do, things to keep track of and so on. Let's check if LHospital works. Square root of 9 is 3, 3 take away 3 is 0, 9 take away 9 is 0. Almost all of these end up being zeros over 0, so it's good to go. And so it's going to be the limit as x tends to 9. Right, now if you want to differentiate the square root of x, I guess I should do that at the side here because it's a bit messy. If you want to differentiate the square root of x, you call it x to the half, right? And its derivative then is power rule. Multiply by the power and reduce it by 1, and then you make it look pretty, okay? So you're comfortable that the derivative of the square root is this guy. In fact, you may have done so many square roots that you've just memorized that one. So I get 1 over 2 square root of x. The derivative of -3 is 0. The derivative of x is 1. And the derivative of this guy is 0. And now I can plug in 9. So it's 1 over 2 square root of 9 over 1 doesn't really matter. And boom. I mean, isn't that nice? We can now get the limits using LHospital's rule. How about this one? The limit as x tends to pi upon 4 of cosine x take away sine x over the tan of x take away 1. Now, before LHospital came along and figured out how to do this would have been impossible, wouldn't it? You couldn't do it algebraically. I mean, wouldn't the best you could do would be a table of values where x got really, really close to pi over 4, and then you do your best guess at what the limit is, right? But it wouldn't be a perfect thing, but it would be the best you could do. Now, if you plug in pi upon 4 for x's here, can you trust me? You get 0 over 0 is indeterminate form, right? And we're good to go. So let's do a little, forgot my little L. So it's going to be the limit as x tends to pi upon 4. Okay, if you differentiate a cosine, what do you get? What's the derivative of a cosine? Come on, guys, I'm not giving you a hard one. Differentiate a cosine.
Negative sign.
You nailed it. And then if you differentiate a negative sign, you get a negative cosine. And this one might tax you, but I hope you can do it. What is the derivative of tan x? That's not so obvious. Derivative
Secant squared x.
That's the one. And the derivative of 1 is nothing. So this one didn't work because when we plugged pi upon 4 in, we got indeterminate form 0 over 0. This should work. Let's find out. It's going to be negative the sine of pi upon 4. Take away the cosine of pi upon 4. All over secant squared pi over 4. Well, I've got it handy. I'm going to need my unit circle. Okay, here's pi upon 4. If you want the sine, it's the y coordinate, so that's negative root 2 upon 2. And the cosine is the x coordinate, so you've got negative root 2 over 2. If you want to get the secant of something, for instance, you want to get the secant of pi upon 4, it's really 1 over the cosine of pi upon 4. So it's the reciprocal of this guy. So it's 1 over root 2 over 2, which makes it 2 over root 2. So that's what the secant pi upon 4 is, the reciprocal of a cosine. So it's going to be 2 over root 2 squared. Okay. If you've got negative a half root 2 and you take away another half root 2, you get minus root 2. And if you take this guy in the top, you get 4, and you take that guy in the bottom, you square it, you get 2, and 4 over 2 gets you 2. There's your answer, negative root 2 over 2. That means we can use LHospital to find limits of expressions we couldn't before, right? If you go back to week 1 and 2, it was quite limited the things that we could do with the techniques of the time. Now we've got a new guy. I like him, the LHospital guy. How about this one? This is the limit as x tends to 0. And it's going to be a tan of 7x all over a sine of 4x. And if you plug 0 in and 0 in, you get 0 over 0 indeterminate form. So I can use LHospital. It's going to be the limit as x tends to 0. If you differentiate tan of 7x, you do get secant squared of 7x. But technically, isn't it a chain rule, right? And the inside function is 7x. So when you differentiate by that, you get an extra 7. Are you comfortable with the secant squared and then the extra 7? Now, if you do a sine, you get the cosine of 4x times the derivative of 4x, which gets you the extra 4. And now we should be able to get the answer. It's going to be 7 times secant squared of 0 over 4 times the cos of 0, because 7 nothings is nothing and cosine of nothing is nothing. The cosine of 0 is 1, so 4 times 1 is 4. The secant of 0 is 1 over the cosine of 0, which is also 1. So this is still 1, and there's your answer. It's 7/4. How about this fella? LHospital at 0 over 0, that works. So you're going to get the limit as x tends to 0 of cosine x over 1. And that's going to be cosine of 0 over 1, which is 1. Interesting. This one is a challenge because it involves a function that we haven't really spent a lot of examples differentiating, but we should still know how to do it. Yeah, if you plug in 0, you get 0 over 0 again, so LHospital can be used. The bottom's easy. Right, here's the challenge. 7 to the power of t. You differentiate 7 to the power of t, you get 7 to the power of t. Do you get anything else?
Times 2.
I wish it was that one, but it's times something,
Is
but
it
not times t.
times 1?
No. Anybody remember it then? Okay. Times natural log of 7. Go back and look at, I guess, the list of derivatives when we did them, and you'll find that guy hiding. Now, if you do this fella, you get natural log of 4 4 to the t. So if you differentiate a to the t, you get the natural log of a times a to the t. Now, we should be able to evaluate that. The log of 7 times 7 to the 0, take away the natural log of 4 times 4 to the 0 over 1 doesn't matter. 7 to the 0 is 1, so is 4 to the 0. And so the answer is that. And that can be made a little bit prettier by doing that. Let's do an infinity one. Let's do the limit as x tends to infinity of e to the x over x cubed. Now, if you plug infinity in here, you get infinity. You plug infinity in here, you get infinity. Infinity on the top over infinity on the bottom is also indeterminate form, so we can use LHospital. Something a little different happens this time. You differentiate e to the x, you get e to the x. You differentiate x cubed, you get 3x squared. Now, if I plug infinity in for x here, don't you still have infinity over infinity? Right, so no good. Well, LHospital says if it's no good, just do it again. And then try it. Okay, I did it again. I differentiated and I got that. And when I plug in infinity, I get e in infinity. I get infinity on the top. I get infinity on the bottom. Still no good. I'll just do it again. Each time I do this process, do you notice that at least one of the terms gets simpler and simpler? In this case, the bottom. Now, I can plug in infinity this time. And e to the infinity is infinite. And infinity divided by 6 gives me infinity. So the limit of this is infinity. And it's okay to have infinity as an answer. Any problems with this? Are we good? Cool little trick, isn't it? And you might be thinking, why didn't you tell us how to do this in week 1 and week 2, whenever this happened? Well, don't you need to know how to differentiate things to do this? So that would be the cart before the horse. Going to give you one to try. This is a version of question 9. It's going to be the limit as x tends to 0. Go for it. You got a minute and a half, 90 seconds. Okay, let's go for it. Differentiate e to the x, you get e to the x. Differentiate this guy, you get negative e to the negative x. So general is e to the negative x times the derivative of negative x, which is -1, and the number disappears. This guy becomes e to the x, take away 1. If you plug 0 in here, you end up with 0 over 0, which is indeterminate form. So we will just do it again then. If you differentiate this guy, you get e to the x. If you differentiate this guy, you now get plus e to the negative x. And if you differentiate this guy, you get e to the x. I'll put in 0 here. Well, -0 is still 0. Nice clean answer, 2. So let's show you some, I guess, well, maybe not trick questions, but situations you have to be a little bit more careful about. So here's my first one. I'm going to do the limit as x tends to 0 of 2x cubed plus 1 over 2x cubed plus 5. Now, you notice that I kind of, maybe you think I'm overdoing it, that I'm always checking that it's indeterminate form. Now, if you plug 0 in here and 0 in here, can't you get the answer? It's 1/5. So you might think, well, no big deal. If I did LHospital, I'm still going to get a 5th. I'm just going to spend a bit more time getting there. Let's see what happens if I apply LHospital to a situation that is not indeterminate form, which this one isn't. Well, you're going to get the limit as x tends to 0 of 6x squared, that doesn't count, over 6x squared. Wait a minute, isn't that just 1? Do you see that you can use LHospital and you will get an answer? What is annoying isn't the answer the wrong answer? So if you're wondering, why am I saying keep checking in the indeterminate form? See if you just do another LHospital because you weren't paying attention. Couldn't you overshoot the answer and do it when you shouldn't be doing it and get the wrong answer? So every single time you do LHospital, and even before you do it the first time as well, check that it's indeterminate form, 0 over 0, infinity over infinity. So that's the first little idiosyncrasy. The next one, trig, is a big example of this type of situation. This is where it happens a lot. I've seen it in other polynomials sometimes generate this problem. Doesn't look like a problem. If you plug in 0, it is 0 over 0, indeterminate form, no biggie. Now I'm going to do LHospital. Okay, if you differentiate 2x, you get 2. If you differentiate the sine of 2x, you get the cosine of 2x times a 2. Okay. Differentiate that guy, you get a 2. Differentiate a tan, you get a secant squared of 2x times a 2. Are we good? Now, if you plug in 0 in here, you're going to get 2 take away 2, 2 take away 2. It's going to be indeterminate form. So I'm going to do LHospital one more time. If you differentiate 2, you get nothing. If you differentiate 2 cosine 2x's, you get a negative, so the answer is now positive. You'll get a sine of 2x, so you get an extra 2, so you end up with 4 sine 2x. Are you comfortable with that derivative? Ends up being 4 sine 2x. If you differentiate this bottom guy, that guy is 0. The next one is not so pretty. I need to differentiate -2 secant squared 2x. And I'm going to call it -2 the secant of 2x squared. I'm emphasizing the square. So when I differentiate it, it's going to be a chain rule. So it's going to be multiplied by the power, reduce the power by 1, followed by the derivative of the inside function. The derivative of a secant is a secant 2x tan x, 2x, followed by the derivative of 2x, which is times another 2. So the derivative is -8 secant squared 2x times a tan of 2x. It's pretty ugly. I'm now going to take it and I'm going to put it in this expression here. Now, if I plug 0 into this, I'm going to get 0 over 0, which you might think, oh, well, just keep going. Well, if you think about it, isn't this going to just get uglier and uglier and uglier every time I differentiate it? And that would be a dead end. So you might think, well, what else can we do? Well, we can use trig identities. So -8 secant squared 2x tangent to 2x. And 4 sine on the top. Right, let's take the bottom. It's -8, 1 over cos squared 2x. And the tangent is the sine of 2x over the cosine of 2x. You still with me, guys? Now, if you take the bottom and you combine these guys, what you now have is -8 sine 2x over cos cubed 2x. Now, if you have a fraction in the bottom, can't you just basically take its reciprocal? And so what that becomes and that's a -8. That guy. Now, if we look really carefully, don't those cancel? And don't those partially cancel? So what am I left with? I'm left with a cos cubed 2x over a -2. Now I can plug 0 in here because the cosine of 0 is 1 and 1 cubed is 1. And so the answer I get is -1/2. So I didn't use LHospital once we got there. What I had to do instead is rearrange this guy, do a whole load of cancelling, get it down to its simplest form, and then plug in the 0 and things came out okay. Now, is that a typical thing? Nah. But if you see a trig expression, and it looks like if you try to do LHospital again, that it was going to get worse, and I think it's pretty clear that's going to be really horrible when you differentiate it, then that would be a good candidate for doing what I just did here. But if it's just sine x plus cosine x, can't you differentiate them a lot and it's not going to get any worse, right? It's going to be fine. Any questions? We like LHospital. Allows us to find all sorts of limits that we couldn't in the past. Let's just pick somebody then. I get one in front of me. This is 11. They want us to do the limit as x tends to infinity. And it's going to be the natural log of x squared. It's kind of fun. Over 3x. And yep, it's indeterminate form, so I can use LHospital. The bottom is easy. Okay. We are going to differentiate the natural log of x squared. So that is definitely a chain rule. And this here is my inside function. So I'm going to get 2 lots of the natural log of x to the power of 1 times the derivative of the natural log of x, which is 1 over x. All I'm doing in this line is a little bit of style points. Right, just making it a little bit prettier. Should always do that anyway if this helps. Now, if I plug in infinity in here, don't I still have infinity over infinity? So it's still indeterminate form. So I'm now going to do LHospital one last time. That guy is 2 over x, and this guy is 3. If you differentiate 2 log x, you get 2 over x. If you differentiate 3x, you get 3. And this I can plug infinity into. Okay, what number will you get from 2 divided by infinity?
0.
And 0 over 3 is 0. So the answer to that limit is 0. Okay. How about this one? So version question 12. It's a limit of x squared sine x divided by the sine of x, take away x. And yep, it is 0 over 0, so we're good. LHospital can be used. Differentiate sine x, you will get cosine x. Differentiate negative x, you will get negative 1. Of course, if you want to differentiate the top, you recognize that's going to be a product rule. So its derivative is f dash g plus f of g dashed. That's 2x times the sine of x plus x squared cosine x. So we have 2x sine x plus x squared cosine x. And I'll plug in 0 and it's still indeterminate form. It's still 0 over 0. This doesn't look good, but it is actually going to be okay. Would you agree that the top is getting ugly? It's getting messier every time. Would you agree the bottom is slowly getting nicer? And for that reason, I'm going to do LHospital one more time. I'm going to give it a chance to figure its, to figure out the result. Oops. So it's going to be just sine x, and we're going to have to differentiate 2x sine x and x squared cosine x. And you're just going to trust me on this. It's negative x squared sine x plus a 2x cosine x plus 2x cosine x again plus a 2 sine x. Just trust me that that's what the derivative of those two things are. Now, this becomes Well, what you got? You got this guy and this guy, so that's 2 take away x squared sine x, and this gets you a 4x cosine x. You okay so far? Now, if I tried, if I plugged in 0, if I tried to just calculate the thing, I'd get a 0 over 0. But I don't want to keep LHospital in this, if there is such a verb, because I can tell this is going to go massively ugly. So I'm going to see if I can make things nicer. I've got this guy plus this guy all over sine x. Okay. So there should be a way that we could work on this. Couldn't I separate it out? Like that. Great. I could do that. Now, that means that this fella just ends up being that guy. And this fella, well, can't really do much with that. This fella, when you plug in 0, gets me 2. And this fella here, I'm now going to do LHospital on again. But would you agree it's a much nicer, simpler fraction that I'm doing LHospital on? Otherwise, wouldn't I be doing it on this guy up here? So let's see what that fella gets us. So if you do LHospital on it, you get the limit as x over 0. The bottom is cosine x. You get 4 cosine x's plus 4x sine x. And then I'm going to split it again as a 4 cosine x over a cosine x plus a 4x sine x over cosine x. And now I have essentially the answer. 4 plus 4x tan x. I can plug 0 in here. 4 times 0 times the tan of 0, which is 0, is 0. So all you get is 4. So that guy is 4. So that guy is 6. Sneaky, but cool.
Are there certain indicators that would like how to stop?
When to stop doing it and when
Yeah, and then
to
also
take
when
over.
to not split it or when to split it.
It's an experience thing, which isn't very helpful because you've never had much experience of them. But the more you do, the more you'll recognize that there are some clues. It tends to be in trig that this process works, right? You're not really going to do it with x cubes and x squared. They work their own way. So when I do that, I tend to look at top and bottom. Are they getting uglier and uglier? That's normally a good sign for me to stop doing LHospital and trying to just do some algebra on it. Now, as you notice, when I did some algebra on this one, I got a good bit and a kind of uglyish thing left over. But after I did one more LHospital on it, I said, okay, stop, let's try it again. Oh, came out good. So the minute you see the top and or bottom getting uglier and uglier, you know the next derivative is going to be really, really messy. You should probably not do LHospital and do some algebra on it. Maybe you'll get the whole thing to work, would be great. This is like the ultimate version of horrible, right? Most of them aren't as bad as this, where you could get one of them to come out good and the other, at least it's nicer. So, give LHospital another shot. Oh God, it's getting worse again. Okay, let's split it apart, see what we can get. Finished. Now, if you try algebra too early, like if you try it after one, you'll know it's not going to work because you'll, turn everything into sines and cosines and nothing cancels, nothing simplifies. So you'll just say, oh, well, okay, I'll do LHospital one more time. Because for instance, in this one up here, couldn't I have stopped there saying, oh God, look how ugly that is, it's going to get even worse. But if you try to do any algebra on this, can you see that there's nothing good going to come out of it? I mean, you can't see anything to do. So you just have to bite the bullet and say, oh God, look at it now. I don't want to keep doing this. Well, you didn't, right? So try it. If it ain't working, LHospital it and then try it again. It has to be doable or the question's not fair, right? That's bottom line. This is a perfect time to finish. So last night,